Section 9.2, Series and Convergence, Part 1. Now that we've talked about sequences, the main idea for this entire unit is going to be infinite series. Now, an infinite series is basically the sum of an infinite sequence. We have all of our terms in our sequence, but instead of just listing them out and dividing them out by commas, we're going to add all these terms together. So instead of being a list of values, it's going to be a sum. Now again, these are infinite series, which means that the number of terms in the sequence is infinitely large. N goes basically from our first term all the way to the infinite number, right, it may approach. Now, the goal in our unit here when looking at infinite series is generally talking about whether or not they converge. That's the big idea. So the most common thing and situation that you're going to see is here's a series, is it convergent or divergent? So we're going to begin by looking at what that means, but more importantly, as we kind of go through this section, we're going to be looking at different types of series, right, different special ones, and ways using them that we can determine whether or not they converge. And again, the idea at the end of the day is that given any sort of series, we can use these tools based on the different styles of series that there are to determine convergence. And what we'll discover is that when we have series that converge, we're going to be able to accomplish some of the goals that we're looking at in using them in calculus. So to begin, let's talk about what it means for the sum of an infinite sequence, right, to actually converge. So to do that, what we're going to do is consider what are called partial sums. Now obviously when we look at the notation here, we're adding an infinite number of terms together to make the series. To figure out whether or not it converges, we're going to look at partial sums, which are just part of the sum. So maybe it's the first 2 or 3 or 4 terms in the sequence added together. And by looking at what the sum does, right, what these different sums are as we, add more and more of the terms together, we get a sense or an idea if the series converges to a value. So to illustrate that, let's look at an example, right? Let's, consider the idea that, we have, and we're going to use lowercase s for this, s sub 1. That means we're going to take the first term in the series. Okay, there's that. Now, if we say the second partial sum, that means we're going to take the first term and add it to the second term. And then to find our third partial sum, we take our first term, our second term, and our third term and add all those together. And we can continue on in this process. What we're looking at is, okay, this is the sum of the first one. Whatever number this is, right, this is going to give us the sum of the second one. This number here is a different number. Looking at these numbers themselves as a sequence, we want to know whether or not it converges. And if we notice that as we continually add more and more terms in the series, that these values, right, these partial sums, if they're converging and their limit goes somewhere, then the conclusion we can make is that the series converges. So in other words, we can say that if the sequence of these partial sums converges, again, basically doing the limit of those partial sums, almost like their own sequence, if that goes to a number, then the series must go to that number, and therefore that is the sum of the series. Okay, that's something we can look at. So to give you a little example, let's consider this. We're going to determine whether or not this series converges or diverges in a very generic way. I want to be clear that what I'm showing you now isn't always really the method we use, but instead we'll have special, methods and things we can do, different rules, different techniques, depending on what the series looks like. But this is just going to give us a general idea of what we're accomplishing when we do all those special things and rules that we're going to learn throughout the unit. So first off, in this case, let's just examine what it looks like, to add these things together. So in this case, if we wanted to look at the first partial sum, that means we just plug a 1 in and we go with the first number. So in this case, it'd be 1/2. Looking at the second partial sum, we're going to take our first number, 1/2, and add it to the second term. Well, plugging a 2 in gives me 1/4. So obviously, if I take 1/2, 1/2 plus 1/4, that equals 3/4. So if I find the third partial sum, that's going to be 1/2 plus 1/4. Plugging a 3 in is going to give me a 1/8, so we'll add that number on. And altogether, that partial sum equals 7/8. And we can continually do this and do this and do this, okay? So what we notice, of course, is, or what we're looking for, I should say, is, we have this number, then this number, then this number. Does that converge on something? So we can view it almost like its own sequence. The first sum is this. The second sum is this, the third sum is this, and so on and so forth. And we want to understand, does it converge? So obviously what we want to do is come up with a way to figure that out. So what I want to do is come up with a rule, right? That's going to help me understand what's going on. Now, I only have 3 terms, okay? And again, if you are unable to see the pattern that I see, don't be afraid to give yourself more. I can just, with these 3, pretty much understand what's going on. But again, you can check as we go through this. So what I notice is on the top, we go 1, 3, 7. On the bottom, we go 2, 4, 8. On the bottom, it's pretty obvious that the term is basically powers of 2. On the top, it's always going to be 1 less than that, so we're going to call this 2 to the n minus 1. And again, you can verify that by looking at more and more partial sums, but as we keep adding more and more terms of the series, these are the values it goes to. So these are the sums, and what we're looking at, of course, is what do these sums do as more and more terms of n are added to that? So we're going to, like before with sequences, say, well, what's the limit as the number, of course, goes to infinity of these sums? Because again, this sequence here describes that. Well, if we go through L'Hopital's rule, because clearly this would be a determinant, it tells us that this goes to 1. So I skipped that step, but I did do L'Hopital's rule and work it out. We did one very similar to this, and this goes to 1. So what that tells me is, first off, the series converges, and not just that, it converges, to 1. Right? So then, therefore, our conclusion is the sum of the series, right? We literally take the first term all the way to the infinite term. If we add all of these together, it goes and equals the value 1. Now, again, this method isn't exactly how we're going to do many of the different types, but again, starting now, as we kind of move through the unit, we'll be looking at different and special types of series based on how they're described and come up with methods to come to this conclusion. It isn't always feasible to simply do this process. It may be very difficult, in fact, but there are rules and different techniques based on different styles of series that we can use to determine whether or not they converge. Now, the first special type of series that we're going to look at is what's called a telescoping series. Now, it's important to understand that not all series are telescoping series, but this will be the first kind of special one we look at, so we at least have one sort of method to determine whether or not the series converges. Now, again, with many other series that aren't telescoping, we're going to learn many more tests and ways and methods to figure out whether or not they converge, but this will just be our first one, so I want to start with an example that is, in fact, a telescoping series. Now, the reason a telescoping series is called that is because when you lay out all the terms, what we discover is that almost every term will cancel out with the one before it or after it, or at least one's pretty close next to it. Okay, it doesn't have to immediately precede or follow it, but pretty close. And because a lot of these things all end up canceling out, we can kind of understand and get a really easy sense of where the series goes. Now, again, the thing about telescoping series is that these are a special type. Not every series falls into that. The other frustrating thing, of course, is that telescoping series don't have a set form. Many of the other special types of series that we're going to talk about, they look a certain way. We're going to know, hey, this is that type, this is that a way we can figure it out. Telescoping series don't exactly have that, but what I will say is that when you're examining telescoping series, you're going to have a fraction and one that you can kind of break up into a difference. And we're going to do that using partial fraction decomposition. So if you're trying to determine whether or not this could possibly be a telescoping series, typically it's going to be one where you can decompose it and then look at it as a difference so that when you lay out all the terms of the series, you can see things that are going to be canceling out. Now, when you do that and you do lay it out, you're going to look for those a pattern, right, in the remaining terms. And then with that pattern, you can then, of course, take the limit to infinity and figure out kind of if it's converging on a point and therefore having the series converge. So looking at our first example, we do have a fraction, and again, this is one that we can use partial fraction decomposition to take care of. So first thing what I want to point out is if I take the 2 over 4 squared minus 1, and I do partial fraction decomposition, I can get 1 over 2n minus 1 minus 1 over 2n plus 1. Now, again, for this to work, really to get that convergence, you're looking to usually have a difference in here to make sure that things are going to cancel out. If there's a plus sign here, you may not get that sort of thing, things to happen. So you want to make sure for the most part you get a minus in here. Now, the next thing, of course, is we want to just kind of lay out what that partial sum sort of looks like and then kind of identify a pattern. So in this case, the nth partial sum is going to look like this. Okay, if I plug a 1 in, and again, this entire expression is where you plug the 1 in. That means the first term is going to be 1 minus 1/3. Okay, and then we add the next term. Plugging 2 into all of this is going to give me 1/3 minus 1/5. Plugging a 3 in, the third term is going to give me 1/5 minus 1/7, and so on. Okay, and we could keep going dot, dot, dot. And so what we're doing is kind of looking for a pattern. Now, what I like to do, of course, is say dot, dot, dot. And because I'm just writing this down, as the nth partial sum, I'm going to write the nth term here just to give me a sense of maybe where it would end, depending on what number I stop at. So the nth term would be obviously 1 over 2n minus 1 minus 1 over 2n plus 1. So whatever sum I want to do, whatever partial sum, this is what it's going to look like. This is first term, second term, third term, up into whenever I stop. What I'm trying to focus on is what things maybe cancel out, right? Because obviously if I can figure out the pattern of things that are going to cancel, no matter how big of the sum I want to make it, right, I can figure out maybe where this thing's going. So what I notice right away is I have a negative 1/3 and a positive 1/3. Those are going to cancel out. So these two, they cancel out. Likewise, the negative 1/5 and the positive 1/5, they cancel. And that's kind of what we mean by the terms cancel out with preceding or following terms, right? One's close to each other, either or right next to each other or within a couple terms, they cancel out and make 0. Which means this pattern is going to keep going, keep going, keep going as far as we want to go. So if I continue my partial sum up into whatever term this is, that means that wherever I stop, this term and this term are going to cancel. That always happens from one term to the next. So wherever I stop, this is what's going to be left, right? I'm always going to have a 1 to start with. These all cancel. And then you're left with minus whatever that last term is. So what I can basically say is that, to simplify this, the nth partial sum really is going to equal 1, everything else cancels, minus wherever we end. And again, that last term is going to look just like that. So for us to figure out whether or not the series converges, let's just look at the limit as our n becomes infinitely big, right? We're going to look at what does the infinite sums, right, as a series, the sequence, right, of all these different infinite sums, where do they go? So in this case, if we do the limit, that means we're doing the limit as n approaches infinity of 1 minus 1 over 2n plus 1. And clearly, as n becomes infinitely big, the second term just goes to 0, and this goes to 1. And because the limit exists, right, that tells me that, the sum is going to 1, and therefore, more importantly, our conclusion is that this infinite series, right, in this case, the sum from n going from 1 to infinity of 2 over 4 squared minus 1, we can say that this equals 1, and more importantly, converges. Now again, because not every series is a telescoping series, we want to study as many different types of series and as many different tests to figure out, whether any series is going to be convergent or not. The second one we're going to look at is called a geometric series. This is one that you've actually seen before because we studied these and looked at these in Algebra 2 and pre-calculus. So these should not be super unfamiliar. So in this case, as a reminder, a geometric series is a series that, to go from one term to the next, we keep multiplying by this common ratio, okay? So we often write the rule to look this way. Now, this one is one that has a certain way that it looks. So visually, you're going to look for this sort of setup to recognize, hey, this is a geometric series, so I can apply the rules for that to determine whether or not it's convergent or not. So clearly, this is what's going to look like. Now, one thing I do want to point out is they sometimes start at 0, which is fine, but they don't always necessarily start at 0. In fact, many geometric series may begin at 1. Now, when that's the case, you basically have a number times r, except it's going to be raised to the n minus first power. Okay, this actually is probably a little more familiar. This probably is how we wrote it in pre-calculus and Algebra 2, but either way is fine, okay? What we have to understand in this form is that whether you write it this way with n starting at 0 or this way with n starting at 1, a is the first term, okay? Because when you plug a 0 in here, that's just r to the 0. Again, that's just a times 1. When you plug a 1 in here, again, producing r to the 0, it's a times 1. So a is the first term in the series. After that, again, you just multiply by r over and over and over again to generate all the terms. So these are the two different ways to write it, okay? And again, this may be more familiar with you, but your job is to recognize this scenario. Another common thing you might see a lot is they'll put parentheses around the r, okay? So you might see that a lot. But at the end of the day, it's your job to look at a series like this and recognize this is geometric. Okay, so because we're going to recognize it's geometric, as you can see right here, we have a rule to determine right away whether or not the series converges, which again, that's the big deal. That's our goal in this unit. So if the absolute value of r, okay, the number we multiply by over and over and over again, right, the thing being raised to a power, if the absolute value of that number is less than 1, then we know the series converges. If that's not the case, then it diverges, okay? Now, the really nice thing about this rule is that this rule does tell us what we need to know to tell if it does converge, and obviously the opposite when it diverges. I bring this up because as we move forward through the unit, there are going to be other rules and tests that we look at for different types of series, and sometimes those rules and tests tell us when things converge, and may not tell us when things diverge, or vice versa. So this is a really nice rule because it does cover both, things, right? It does tell us what we need to know to say it converges or whether or not it diverges. It does answer the question. Again, other tests and other rules down the road actually might say, listen, if this is true, then it is convergent, and if not, it may just be unknown, right? It may be inconclusive. We may have to do something else, right? Maybe apply a different test or do something else to figure out the answer. So some rules will cover all the bases. This is what converges, this is what diverges. Some rules may just give you one or the other and be inconclusive otherwise, and you may have to walk down another road, okay? So I want to highlight why this is such a nice rule. We get both. Now, in addition with geometric series, because we studied this before, and this is not true about many of the other types of series we're going to study, but for geometric series, we actually have a formula to find the sum of them as well, okay? So, and this is coming from Algebra 2 in pre-calculus. So while we're probably not really going to look at the full sums of most series that we study, with geometric ones, because it's a nice easy formula, we're going to be looking at it. So again, if the ratio that we're looking at, if the absolute value of that is less than 1, it does converge, otherwise it diverges. But in addition to that, if it converges, okay, so we have to check that first, any convergent geometric series has a sum of a over 1 minus r. Now, I'm writing a very generically here because I don't know how this looks, but to be clear, this is the first term. So it might be wise to really look at it like a sub 1 divided by 1 minus r, okay? And that calculation, like we did in pre-calculus, tells us when infinite geometric series, what that sum is going to be if you add all the terms together, okay? So again, you want to recognize it's geometric, and then, of course, looking at whatever the value of r is, you can tell right away if it converges or diverges, and if it converges, we have a quick way of determining what the sum is. So let's try a couple of examples. Here, again, you can clearly see just by the forms that these are geometric series, okay? So what you want to notice with all of these, of course, is that what's your a, what's that first term, and then what's your common ratio, what's the r. So in this case, we're starting at 0, so it makes sense we have an n up here. But in this problem, we know that the a is equal to 2. That's our first term. Again, plugging 0 in gives us 2. The common ratio here is -1/2. So this geometric series is, 2. So starting at 2, and you keep multiplying by -1/2 over and over and over again. This does produce positives and negatives and so on, but it still may converge or diverge. In this case, what I know is that because r is -1/2, if we look at the absolute value of it, we can say, well, the absolute value of -1/2, that's just equal to 1/2, which is always less than 1. So our conclusion here is going to be that it converges. And again, that's always going to be the biggest deal as far as looking at series in this unit. We want to know whether it converges. Now, again, just with geometric series, if it does converge, we'd like you to calculate the sum, right? That'd be nice to know. So in this case, the sum of the series is going to be that formula, okay? So in this case, it'll be our first value, 2, divided by 1 minus our r value. Now, this is where you do have to put the negative in there, so be careful. It's going to be 1 minus that -1/2. And when you work it out, the sum of this series is going to be 4/3. Now, again, the sum only exists if it converges. So as we take 2 and keep multiplying by -1/2 over and over and over again and add all those numbers together, when n becomes infinitely big, all of those numbers converge together and as a sum create 4/3. Now, in our second example, we can see pretty clearly, right, in this case that our a is going to be a 5. That's our first term. Our common ratio r is 1.52. Now, right away, what should jump out at you, of course, is that if you look at the absolute value of 1.52, clearly that's bigger than 1. And because it's not less than 1, we can make the conclusion that this geometric series diverges. Because it diverges, it has no sum. Now, in our third example, it does look a little bit different because if you don't have the parentheses, maybe it's not as obvious what a and r may be, but you can always choose to rewrite this. So when I look at this rule, instead of seeing it this way, I'm going to look at this as 3, and this is also going to be 1/2 raised to the n. Okay, and it's okay to look at it that way, even though it's just 2 to the n, because 1 over 2 raised to the n is the same thing as 1 to the n over 2 to the n, and clearly 1 raised to the n will always be 1. So this is actually kind of what the rule looks like. Now, with that in mind, we can clearly now see that the a is going to be a 3, right? The common ratio is going to be 1/2. And since the absolute value of 1/2 is less than 1, right, then we can say right away that, again, this series converges. And since it converges, we can find the sum. So in this case, the sum of this infinite geometric series is going to be the first term, so 3, divided by 1 minus our r value, which is 1/2. And when you punch that up, it has a sum of 6. Now, our last one really doesn't look too much different, except to say the fact that this starts at n equals 1. Now, because of that, you want to be really careful to understand what the first term in the series is supposed to be, okay? So because this starts here at 1, we've got to have a really clear understanding of what this looks like as we move it off and have that value happen. So when we plug a 1 in, the first term of the series isn't just 2. And that's really the only difference between this and the other ones. You don't really get A1 right away. So while I wrote A here, and that always stood for my first term, the first term here is a little bit different, okay? So you have to literally just say, well, when I plug in 1, what do I get? Well, plugging in 1 gives us 1/4 times 2. So that means in this geometric series, the first value is going to be 1/2, okay? So you have to make sure you realize when they start at 1 and they just have an n up here, that's going to be, what it is. Now, clearly, if they use n-1, yes, this would be A. But as you can see, just to be a little different, right, they decided not to do that. And that's fine. We still have a number that we start with. We're still always multiplying by 1/4 over and over again. It is geometric, but I'm just saying sometimes they get different in the way they're set up. So we want to be careful to understand A, we're always going to let be that first term. So if this is just an n, plug a 1 in, see where you're starting at. Now, the r still is going to be that number that we're, again, multiplying by over and over and over again, so that's going to be a 1/4. So what we're going to do here is figure out, okay, where's this thing going? Well, clearly, when you look at the absolute value of 1/4, again, that's going to be less than 1, so therefore we can say that it definitely converges, and therefore, if we want to find the sum of the infinite geometric series, we'll take our first term, which is 1/2, and divide it by 1 minus 1/4. And when you work that out, the sum is 2/3. Now, the last thing we want to talk about today is just another test, right? But this one is very special because this is a test for divergence. And one thing I want to really emphasize, and I mentioned this earlier when we talked about the geometric rule, is that this test can tell us if a series diverges. However, it cannot tell us if a series converges. So basically, there's only two outcomes. Either, yes, I know this is a divergent series, or I don't know. It's just going to be inconclusive. And that's really important to realize, because some of these tests, like this one, have limitations, okay? So while the geometric test told us yes or no, whether it converges or diverges and kind of covers all the outcomes, this doesn't. So in the nth term test for divergence, and again, you can see it right there in the name, it will identify whether or not a series diverges or we don't know. Okay, those are going to be the two outcomes. Either, yes, it diverges. It will tell us that right away. We know it's a divergent series. Or it's going to say, it's inconclusive, try something else. You're going to have to go to another test, another method to figure it out, okay? So it's either inconclusive or it confirms the series to be divergent. So basically the theorem is, and this is how it works, because we know convergent series, right? When that happens, we know the limit has to go, to 0, right? That's always going to be the case, right? Because if you think about a series converging, then obviously, as you get bigger and bigger values, it's going to have to, creep in on something. The numbers basically have to get smaller, if you will. We know that to be the case. Now, remember, the converse isn't true. Just because you go to 0 doesn't mean that's the case. So it does only work in this direction. But because of that, we can derive from that the nth term test for divergence. So what we can say is this. Because we know that all convergent series have a limit that takes you to 0, again, the values you're adding together have to get smaller, otherwise it wouldn't converge, then what we know is if the limit as n approaches infinity of the rule, if it doesn't equal 0, then it can't converge. Again, it diverges. It must. Okay, so essentially we're using what's called the contrapositive. We're flipping it around and using the opposites. This is the only way it's going to work, though. Okay, so to be clear, if you do the limit on the rule and it goes anywhere but 0, if we know it doesn't equal 0, then we know for a fact the series must diverge. Now, if we do the limit and it goes to 0, we don't have a conclusion. Okay, so to be clear, it's inconclusive. We don't know. You cannot say that it converges, and that's really important. This is probably one of the most common mistakes found in this area of calculus. When using this test, which is a really common test to use, making that assumption, okay? So again, one last time, the nth term test for divergence will either identify it to diverge or be inconclusive, okay? This test cannot identify convergence. It only identifies divergence, or it fails and you have to go use some other test or method. Okay, so again, it's real simple. We'll do the limit. If it doesn't go to 0, right, if it goes anywhere else, whether it's a number or the limit doesn't exist, if you will, that's going to be, okay, it diverges. But in the case that the limit does equal 0, we just have to say we don't know, right? It's inconclusive. And to be clear, there are many, many, many series that do go to 0. So clearly this test is not nearly enough to answer many of our questions, and that's one of the reasons why we're going to learn a lot more methods and tests to make sure we can tackle those. Because while this one tackles literally every series that doesn't go to 0, many do, and we'll have to deal with those. So let's try this out. And again, right here, just to make sure we're on board, I copied it again. We'll do the limit. If it doesn't go to 0, the series is divergent. Otherwise, it's just going to be inconclusive, right? So we'll just say right now, no conclusion. That's not to say that we couldn't figure it out, but we're not ready because we don't really have a lot of rules and methods yet. So for right now, we're just going to say no conclusion. Okay, so looking at our first example, again, we'll take the limit as n becomes infinitely big. This time, obviously, the rule is 2 to the n. Now again, if we let n become infinitely big, that just becomes infinity. It increases without bound. Clearly, that's not equal to 0. And because of that, we can say that this series diverges by the nth term test for divergence. Now, if you notice, I kind of said why. That's something we're going to really start to practice and get used to. So right now, I wrote down it diverges, or divergence. Not really sure what I wrote there. Let's erase that. So we'll just say diverges, so maybe it looks a little nicer, diverges. A lot of times they're going to ask you to explain yourself, okay? So because the most common scenario, the most common question with series that we're going to look at is, do they converge? You're always going to want to have a reason why. Now, obviously, we're using the nth term test right now, so we can tell that's what we're using. But down the road, when we have many methods and tests and things like that, always write down how you knew it, okay? So in this test, because we know what it is, I'm just going to write diverges. But if this was mixed among many others and I had a lot more tests and things I could use, you're going to want to write that down. So you'd say it diverges by the nth term test for divergence. Okay, let's try this one. So here, again, we'll look at the limit as n becomes infinitely big. The rule is just n plus 1 over n. And again, as you let limit go to infinity, that clearly goes to 1, which is not equal to 0. And again, this is going to be a series that diverges by the nth term test for divergence. Now, to give you a little bit different idea, let's check this one out. Okay, let's do the limit. And what makes this one a little bit different, of course, is that as n approaches infinity, we're going to get a lot of different numbers, but the thing is it just kind of alternates. You get positives and negatives and positive negatives, and really it's just going to be like 2's and negative 2's and 2's and negative 2's and so on. And so when you think about what this does as n becomes infinitely big, it really just oscillates. And what we studied about limits and oscillation is that those limits do not exist. And of course, not existing clearly does not equal 0. So again, we can make the conclusion by the nth term test for divergence that this series diverges. Now, this last one here, again, we'll do it one last time, as n becomes infinitely big, is going to be of 1 over n. But again, in a fraction, if the denominator here becomes infinitely big, it does go to 0. And because, of course, it equals 0, that means that I can't say it diverges, but I also can't say it converges. So in this case, this is just going to have to be no conclusion. Now, I know you might say to yourself, well, clearly, if we're adding smaller and smaller numbers, it's going to converge to a number. Well, that's not necessarily true. There are many series that have this idea, the limit of the rule does go to 0, but they still diverge. In fact, to let you know, this one actually is one that does. We're going to look at this special one here very soon, but this one actually is divergent. Okay, so even though I'm writing no conclusion, if we skip ahead a couple sections, we're going to learn this is actually divergent. So again, to emphasize, this test, the nth term test, it can identify divergence, just like here, right? If it doesn't go to 0, yes, it's a divergent series. But when it does go to 0, we just don't know. Maybe it does converge, maybe it doesn't, but this test, the nth term test, it doesn't provide a conclusion, okay? So this right here, all we can say right now, based on our limited things that we know, we're going to say this is no conclusion.